Let's look at deformation in axially loaded elements. Okay, today we will not have a lot of theory, though basically you have several equations to remember. Just to calculate the deformation in axially loaded element, you may have simple axial elements. You may have systems connected, system of connected axial elements. You just put different sections together. But they may have different properties, different modulus of elasticity, different lengths, different cross-section areas, etc. Okay. You may also have an axial element with variable sections or loading. Okay, so the basic equation is just this one. Just to give you a single piece of axially loaded elements. How do you calculate deformation? We will use loading F times the length L over modulus of elasticity times the cross-section area. So how did we get this equation? This is a very simple derivation. You start from the delta, right? Just like we solved a previous example. Let's analyze it and see how to find it out. And how do you calculate delta? How do you calculate delta? It is based on its definition. We use based on the definition of a strain, right? We use strain times what times L, right? And how do we calculate strain? Strain the stress over E. Right? E is a constant. So how do we calculate stress? How do we calculate stress? Stress is F over A. Right? So you can see, let's go backward. Substitute this equation into this one. You will get epsilon equals F over EA. Right? Substitute this one into this one. You will get epsilon delta equals F L over EA. Right? So we derived this equation. So this is just a basic equation. This basic equation for calculating the deformation in axially loaded elements. And the second equation will be easy to understand. See, if you have different sections like section 1, section 2, section 3, and you want to know the overall deformation, you just calculate their specific values of deformation, add them together, right? So this sign is just sum. You add the different components together, get the overall value. And for the elements with variable section or loading, meaning that the F is not a constant, it's not just simply adding several sections, it's a distribution. We know the F is a distribution, or A is a distribution. The cross-section area is a distribution. Sometimes the E may also be a distribution, but we normally do not consider that. Okay, just no matter which one had a distribution, not a constant, right? We can do an integral. I can do an integral as shown here. I just you get a F distribution of F over E and distribution of A times dx. Right, the dx replaces the L. Since this is just a incremental, a very small unit along the direction of L. Okay, these are the three equations. I think if you can remember the first one, you can easily remember the second and the third one. And the first one is easy to understand. If you cannot remember it, you can just derive it by yourself, as I just shown here. Right? So the deformation has sign conventions. It's easy to understand. Right? So elongation means positive, and the shortage meaning negative. Okay. And a note here, just in these two cases, case 1 and case 2, you can see that in case 1, this element is elongated to the right side, and in the second one, it's elongated to the left side. Okay, and in these two cases, since they are both elongation, so both of them are positive, right? Positive deformations. These are basically all of the theories, and let's go through several simple examples to understand the process, the concepts and the process, how to analyze the deformations in axially loaded elements and axially loaded element systems. Okay, the first example is shown here. You have a column. Yeah, it's strictly speaking, it's not a column, but let's call it a column. This is the column. It has two sections fixed to the bottom, the pink parts. We will assume that at point A you have nothing to happen. Right? So A is a fixed end. Then you have these two sections. AB, we call it section 1, and BC, we call it section 2. Okay, you're requested to determine the normal stress in rod 1. I will skip this step since this is a problem in chapter 1. Right? Then the displacement of point C. Okay, how do you calculate the displacement of point C? Right? You just need to understand something. How do we calculate the displacement at point C? Now we're determining displacement at point C. We will just need to use the equations we just learned to calculate the deformation of part 1 and deformation of part 2. You add them together, you will get the overall deformation of this whole column, and that equals the displacement of point C. Right? So this equals delta AC. And the delta AC, of course, it equals what? Equals delta AB plus delta BC, or delta 1 plus delta 2. Right? So we just need to calculate delta 1 and delta 2 respectively. In the first step, let's calculate delta 1 or delta AB. The cross-section area, there's the equation there, right? The equation lists the equation there. This delta equals what? FL over EA. Right? E has been given. E is here, has been given. And L, we have known that the L1 or LAB is 1.3 meter. And F we have not known, right? This is the internal force. F1 we don't know. So here is a F1 we don't know, and A1 we just need to do a basic simple calculation. Okay? So the A1 is just pi over 4 times D1 square. Okay? So that is pi over 4 times D1 is 50 millimeter, 50 square. So we got 1963 square millimeter. And then just how can we determine F1, the internal force in part 1? How to determine it? Free body diagram. Right? Free body diagram. So you have to cut it from here, and make it free, then add a F1 here, outward. Right? So here you have here we have P. Oh, we have PC. PC is 28 kilonewton, and we have a PB downward, that is 32 kilonewton. Right, then we need to add the internal force F1 here. So very simple equilibrium equation. All right, this is PC minus PB minus minus F1 equals 0. So F1 equals PC minus PB. That is 28 minus 32. That is negative 4 kilonewton. Okay, then the delta AB or delta 1 equals delta AB equals what? It's F1 L1 over E A1. Here you can see that we have derived different, we have determined different values, but their units may be not compatible, right? So we have the A in square millimeter, we have the F in kilonewton, and we have the E in gigapascal. So we have to do some conversion of the units, like to make them compatible. Okay, we have talked about the unit conversions in chapter 1. Right? You should be, I emphasize that again, you should be very familiar with them. We have known that MPa equals 1 Newton per millimeter, square millimeter. So this is the compatible unit system. If you use this system, you just need to convert everything about Pascal into MPa, everything about Newton kilonewton into Newton, everything about cross-section area or length into millimeter, square millimeter. Okay, so this is a compatible unit system, millimeter, Newton, MPa. Right, so we just convert everything into this unit system. You just look at here, F1 is negative 4 kilonewton, so that is negative 4,000 Newton, right? Then times L1 is 1.3 meter, right? That is 1.3 times 1,000 millimeter. Okay. Newton here, millimeter here, right, over E, the E is what, 120 giga-PA. GPA is just 120,000 MPa. Times the area A is 1963. Oh, the millimeter, no problem here, right? Millimeter square. So you can see that we have Newton per square millimeter, this is MPa, so MPa gone, so you have only a millimeter left. Okay, so the result here will be negative 0.022 millimeter. This is negative. What does that mean? Meaning that part 1 will be shortened. So the displacement of point B will be downward. Okay, so point B will be downward. Then in step 2, we determine the delta 2 or delta BC. So just we need to just follow a very similar steps. The A2, we just need to determine A2. What is A2? A2, D2 has been given, that is 32, right? So it is a pi over 4 times D2 square. It's a pi over 4 times 32 square. We got 804 square millimeter. Again, just a free body diagram. This one easy, right? Since you have only one thing, which is cut it from here, add F2 here. Right, easily F2 equals what? Equals PC. Right, so F2 equals PC. That is 28 kilonewton. Then we can calculate delta 2 equals delta BC equals what? Equals F2 L2 over EA2. F2 is 28 kilonewton. Right? L2 is just 1 meter, 1 times 1,000 millimeter. Right? Over E is 120,000 MPa times A2, that is 804. Okay, so here we got 0.29 millimeter. So this one is a upward, right, upward deformation. And so finally, what is our delta C? Since we analyzed the delta C equals delta AC, right, equals delta AB plus delta BC, or delta 1 plus delta 2. Right. So this is negative 0.022 plus 0.29. You get positive 0.268 millimeter. Is this upward or downward deformation, displacement? Sure, this will be upward, right? So when you add this PC and PB, at point C will move upward by 0.268 millimeter.